Now, we spent that first bit talking about rates. Rates described how fast a process was going to take place. Now we're going to talk more about destination. Equilibrium is where a reaction ends up. It's not how fast it gets there. Now, equilibrium is achieved when the forward and reverse rates are proceeding at the same speed. Chemistry never stops. Molecules don't say, okay, my reaction's done, I'm going home, we're finished now. Think of an escalator. If you got on an escalator is essentially a moving set of stairs. Let's say the escalator was moving up. Let's say that you decided to go down on that escalator that's moving up. If you match the speed of the escalator, doesn't look like you're going anywhere. Now, the question is, did you actually stop? Are you actually moving still? Yes, your legs are still moving, but it doesn't look like you're traveling any particular distance. That's because the speed that you're moving is equal and opposite to the speed that the escalator is moving, so you stay in roughly this position. You would be in an equilibrium state because your forward and reverse rates were proceeding at the same rate. Now with a chemical reaction, like H2 plus I2 goes to 2HI, we have reactants on the left, we have products on the right. We have a double-sided arrow in the center here, meaning we can go from reactants to products or from products to reactants. Looking at the plot below, if it's 0 down here, this says that I started with 0 HI, with none of it. So I didn't have any products to begin with. So over time, I started with 0 HI. This line kept climbing and climbing and climbing until eventually it levels off. Once it levels off, this is where I've reached equilibrium. For H2 and I2, I started with a certain amount up here. I start using it up, my concentration of H2 and I2 decreases until I get to an area where this curve flattens out. So at the same place roughly, I've reached equilibrium. It doesn't look like at these points like the concentration is changing with respect to time. It's leveled out, it's gone flat. But that doesn't mean that the reaction has stopped. It just means that HI is breaking into H2 plus I2, and H2 plus I2 are forming HI at the same speed. This is equilibrium. It looks like things have stopped, but they haven't stopped. The plot levels out, but chemistry is still happening. Now, looking at this in a slightly different direction. In our previous hill diagram, we started with H2 and I2, and we started with no HI. Here, we start with HI, and over time, it gets used up and used up and used up until we start to level out. Once it starts to level out, that's where we've gotten equilibrium. If we trace it down here, roughly at the same spot, my H2 and I2 concentrations begin to level out as well, so I've reached equilibrium. It's where the reaction has appeared to have finished, but the chemistry is still happening. Now, we do want to be able to put a number to this to treat equilibrium as a quantitative value. And we look at that with the variable K. K is going to be called our equilibrium constant. It's temperature dependent, and it's going to be a ratio of products over reactants. So in general, K equals P over R. Now they're going to be raised to the coefficients of their stoichiometric coefficients from the balanced reaction. So to be able to figure out a K, we need a balanced reaction. If we look at the reaction here, I've got two A's on both sides, and I've got one C on both sides, so we're balanced. Now it's products over reactants, so I'm going to have K equals A2C on the right-hand side. I'm going to put it in brackets, and brackets mean molarity. So it's the concentration of my product over my reactant, which I have A as one of my reactants. My other reactant is C. Here comes the last bit. Now, up top in the reaction, there's a plus sign between the A and the C. When you get to your K expression, there's no plus sign in between your A and your C. Instead, I'm going to be multiplying these. So they're multiplied together. Because I have a 2 in front of my A in the balanced reaction, I square the A concentration. Because I only have a 1 in front of the C, it's just raised to the 1 power. But because a 1 can just be omitted and just still mean a 1, I'm going to leave that out there. The 1 is just assumed to be there. Alright, so we've got our first K expression shown here as K equals the concentration of A2C over A squared times C. Now, this is going to depend on the reaction that you're looking at. It's going to depend on the balanced reaction. So I have to give you a little bit of information if I want you to write an equilibrium constant. Now, let's try writing an equilibrium constant expression. Let's tackle the second question, then we'll tackle the first one. So we're tackling this one first. What's the equilibrium constant expression? Means we have to write our own equation for the reaction above. Start out writing K equals products over reactants. So NO2 is a product, so it goes on the top. And I've got a 2 in my balanced reaction for NO2, so I'm going to square it. In the bottom, I've got N2O4 because that's one of my reactants. And there's only a 1 there, so I'm going to put a 1 as my exponent on N2O4. And again, that's assumed to be there. So there's my expression for equilibrium for my K. But the top question, we have to tackle that also. If we only start with NO2, what gases will be present at equilibrium? NO2 is our product. We make 2 NO2s for every N2O4 that breaks apart. This reaction has a double-sided arrow, so it can go in both directions. Now, up to this point in chemistry, up until this lecture, we've assumed we start with reactants and we make products. But because this is equilibrium, because we have this double-sided arrow, if we just start with only NO2, so we're only starting with product, we're going to make N2O4. So if we only start with NO2, at equilibrium we're going to have a mixture of NO2 and N2O4 because some of the NO2 is going to reverse and go back to reactants and make N2O4. Now, a little caveat to our K. Our K is still a ratio of products to reactants, but we do not include pure solids and liquids in the equilibrium expression. This is a very important point because I see this happen a lot. You can't express the concentration of a pure solid or a pure liquid in the same way that you can a gas or an aqueous. We do include gases, we do include aqueous, but that's because we can express their concentrations through molarity. So if I were to disregard this rule and I was writing the K expression for the reaction above, I would say KCl O2 squared for my products over my reactant, which is KClO4. But in the place of my solids, I have a solid in KClO4, so I'm just going to put a 1. I have a solid with my KCl, so I'm just going to put a 1. It ends up being 1 times O2 squared over 1, which is when reduced, just K equals O2 squared. So, when writing a K expression, make sure to leave out pure solids and pure liquids. Now, pause the video and try writing these expressions on your own. I'll give you a few seconds to pause it, and then we'll go over these together. All right, let's tackle the first one. We've got K equals a ratio of products to reactants. We've got all gases, meaning that everything is included in our K expression here. In the product side, the top, I'm going to have NH3, and I'm going to square it because I have a 2 in front of the NH3 in the balanced reaction. In the bottom, I'm going to put H2 because it's one of my reactants. I'm going to cube it, raise it to the third power because there's a 3 as its coefficient in the reaction. I'm going to multiply that by N2 raised to the first power. All right, that is our K expression for that first reaction. Second reaction, let's take a peek and see if anything gets left out. We've got gas, 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 and gas, so everything made it in. K equals products on top, so H2O squared times Cl2 squared over 4HCl, over HCl raised to the fourth power because of that 4 coefficient times O2. So it's P over R, products over reactants, and each product and each reactant is raised to its coefficient that shows up in the balanced reaction. Let's finish up this last one. Now taking a look at these, I've got a solid. So that's not going to be included, it's just going to be given a 1. Calcium oxide is a solid, so it's going to show up as a 1. CO2 is a gas, so it will show up. So my K is going to be CO2 raised to the first power, multiplied by 1 for that calcium oxide, divided by 1 for the calcium carbonate. That just reduces to K equals CO2 for my K expression. All right, so we can write an expression. The next step is to fill in numbers and use these expressions to be able to make predictions on K. So based on the magnitude or the size of K, we can decide whether at equilibrium we're going to have more reactants or products. In a general reaction, we have one arrow going this way from reactants to products. We've got another arrow coming back from products to reactants. Our K term is a ratio. It's products over reactants. So if K is very big, and our definition of very big, if K is greater than 10, we're going to say the reaction favors products. Now this makes sense numerically. Products are in the numerator, so if products are what we have most of, then P is going to be a big number. If P is a big number, then K is going to be a big number. If K is greater than 10, equilibrium favors the products. If K is close to 1, we're not going to be able to make a call in either direction. But if K is less than 1, equilibrium favors reactants. You are going to need to memorize these 3 cutoffs. Greater than 10, product favored. Less than 0.1, reactant favored. Close to 1 is too close to call. Know those because you're going to want to be able to make predictions based on the values of K that you're going to be calculating. So let's do a little practice. If the equilibrium concentrations of hydrogen and nitrogen gas are both 4 molar, so it gives us H2 and it gives us N2, and the ammonia is 1 molar, so it gives us the concentration of ammonia also, what's the value of the equilibrium constant K? So 2 pieces to this. It doesn't give you an equation. We have to write our own equation. We have to write an equilibrium expression. So K equals my products, which I have 1. It's NH3, and it's a gas, so it's included. And we're going to square it over H2 to the third power, because it has a 3 coefficient in the balanced reaction, times N2 raised to the first power. So there's our K expression. Now we start filling in based on what the problem told us. So K equals my concentration of ammonia, which is in the top, is 1. So I'm going to say 1 molar squared. In the bottom, my concentration of nitrogen and hydrogen are both 4 molar. So I've got 4.0 to the third multiplied by 4.0. So let's type that through the calculator. Take a moment, pause the video, and we'll see if our answers match. Your K value should equal 0.0039, which we have a K value now that we made based on our K expression. And just one point to point out, it gave us equilibrium concentrations to plug into this. It didn't give us how much we started with, it gave us how much hydrogen, nitrogen, and ammonia we had at equilibrium. If you're going to use the equilibrium constant, make sure you're plugging in the values that you had of each chemical at equilibrium. We solved for a value. This is where we get to take a look at what this value means. So this would deal directly with making predictions based on K. Our value is 0.0039. Let's look at where that K falls on the chart. That K is 0.0039, which is less than 0.1. That means equilibrium is going to favor the reactants, which means at equilibrium we have more reactants than products. After things have leveled out and it looks like the reaction's finished, we have more reactants than products in the mixture, because that K is less than 0.1.